In my previous lecture, I defined the new physical quantity called work. Work is the dot product between the force vector that is applied to an object and the displacement over which that force acts. For now, here in this lecture, what we do is we just use that definition to practice calculating work for simple dynamical situations. A little bit later on, then we'll go through exactly the meaning of work, but for now we just treat it as a mathematical definition. Okay, we'll take a look at two specific examples that we've seen before back in the previous unit on dynamics. So let's take a look at the first of those two. An object of mass 2 kilograms is pulled horizontally across the floor with a constant force of 15 newtons. Coefficient of kinetic friction equals 0.4. The object begins at rest and is pulled over a distance of 10 meters. We're going to calculate the work done by the individual forces, and we're also going to calculate what is called the net work done. Now here's a simple diagram of the situation first. Here's my surface. Okay, here's my object of mass m equal 2 kilograms, and the object begins at rest. Okay, we have a coefficient of kinetic friction between the object and the surface below as 0.4. And then I come along and I exert a horizontal force like so. We're going to call this force F pull. This is given to us as 15 newtons. And then I pull the object over a displacement delta r. This is given to us as 10 meters. And then therefore at the end of the problem, the object ends up over here. And it does so at some speed v that we're not going to bother to calculate. Now, in order to calculate the work done by the individual forces, we need to know the geometrical relationship between the force vectors and the displacement vector. So, of course, we draw a force diagram. Now, vertically, we just have the normal force here, and the object's weight, mg, just canceling each other out. And then horizontally, we have F pull like so to the right-hand side. Opposing the motion is the force of kinetic friction to the left-hand side, and ultimately the object will accelerate to the right-hand side like so. Now off to the side, I'm also going to draw here the displacement vector delta r, once again to see the geometrical relationship between the force vectors and that displacement vector. And now we just use the definition of work to calculate the work done by the individual forces. Let's start with the normal force. Okay, now the work done by the normal force is equal to the following. It's the dot product between the normal force vector and the displacement vector. Notice the vector symbol here above the normal force n. And now if you recall the definition of work, that is how you find the dot product, let's go ahead and use the definition of the dot product now to make this calculation. So we take the magnitude of the first vector times the magnitude of the second vector and then multiply by the cosine of the angle between the two vectors. Notice that the angle between the normal force here and the displacement delta r is 90 degrees. Cosine of 90 degrees is equal to 0. So no work is done by the normal force. Now, off to the side in your notes, I want you to write down the following question. Okay, what is meant by no work being done by a force? Okay, we'll answer this question a little bit later on, but for now in this lecture, in your notes, I'll be posting these questions as we go. The reason for this is because what you're going to begin to learn here at the beginning of this unit is the mathematical nuts and bolts of energy transfer. And energy transfer is one of the most important physical processes that occurs in nature. Now, of course, from previous courses, you are somewhat familiar already by what is meant by energy transfer. For example, go back to biology class. One of the things that you studied in biology class in cell respiration is what is called the Krebs cycle. And in the Krebs cycle, what you wrote down in your notes, for example, was a series of steps that described that cycle. As you did, what you were writing down was a series of energy transfers. Now, you wrote your notes in that manner qualitatively, that is, without any mathematical calculations. But here, mechanically, what you're beginning to learn at the beginning of this unit is the mathematical nuts and bolts of energy transfer, how you calculate it. And it all begins with the definition of work. We'll see this further as we proceed into this unit. So for now, we'll just pose these questions that we'll answer a little bit later on in greater detail. Okay, next let's take a look at gravity. Okay, so the work done by gravity is going to be the dot product between the gravitational force vector and the displacement vector. Notice the vector symbol above g, acceleration due to gravity. And now once again, we just use the definition of the dot product to make this calculation. So we take the magnitude of the first vector times the magnitude of the second vector, and then multiply by the cosine of the angle between the two vectors, which is in this case 90 degrees. Cosine of 90 degrees is equal to 0. So in this horizontal situation, no work is done by gravity. Okay, now let's take a look at F pole and then the force of kinetic friction. I'll do this on the lower board. Okay, so first of all, the work done by F pole. This is going to be the dot product between F pole and the displacement vector, and then once again we just use the definition of the dot product here as we proceed. So we take the magnitude of the first vector times the magnitude of the second vector, and then multiply by the cosine of the angle between the two vectors. Notice that there is a 0-degree angle between F pole and delta R. They are both pointing in the same direction. Cosine of 0 degrees is equal to positive 1. So then therefore what we end up with here is essentially just force times distance. So if at any time in the past you were introduced to the concept of work as force times distance, technically that's really only the case if the force vector and the displacement vector point in the same direction. And now numerically we have here 15 newtons multiplied by 10 meters. This right here is 150 joules. Okay, with a little bit of practice, making this calculation is easy to do, but as of yet we don't know exactly what this means. So let's go ahead and write the following question in your notes. What is meant by positive work? Once again, we'll answer that a little bit later on. And then lastly, for the individual forces, we now have kinetic friction. So the work done by kinetic friction is going to be the dot product between the kinetic frictional force vector and the displacement vector. So then using the definition of the dot product, we first of all have the magnitude of the first vector times the magnitude of the second vector, and then multiply by the cosine of the angle between the two vectors. Notice that the angle here between F sub k and delta R on the diagram above is 180 degrees. Cosine of 180 is equal to -1. So we pick up a negative sign. Now the work done by kinetic friction is always going to be negative. In other words, there's always going to be a 180-degree angle between F sub k and delta R, because recall that the force of kinetic friction always opposes the motion. Think of the motion here as the displacement vector delta R, so then therefore we're always going to calculate a cosine of 180 degrees when finding the work done by kinetic friction. Okay, now the force of kinetic friction is the coefficient of kinetic friction multiplied by the normal force. And then as we've noted on the diagram above, the normal force is equal to the object's weight. So we end up with this little expression here for the work done by kinetic friction for this horizontal situation. Let's go ahead and plug in our numbers. So I now have negative and then 0.4 times 2 kilograms times 9.8 meters per second squared, and then multiply by the displacement of 10 meters. And this ends up being negative 78.4 joules. Once again, as of yet, we don't really know what the negative sign means, so then therefore let's write the following question. What is meant by negative work? Okay, so with this calculation, we complete the first portion of the problem, which is to calculate the work done by the individual forces. Next, we're going to calculate what is called the net work done. In order to do so, let me do a little bit of erasing here on the board. Okay, now I'm just going to rewrite some of the numbers that we calculated a few moments ago for these forces, because we're going to refer to these numbers again in just a few moments. And now let's get to exactly what is meant by net work. There are two ways to calculate net work. Both ways are important for different reasons. First of all, let me define it for us in the following way. Okay, net work is first of all written in this manner, and by definition, it's equal to the dot product between the net force and the displacement vector. Recall from Newton's second law, however, that the net force is mass times acceleration. So this is the dot product between ma and the displacement vector delta r. So let's go ahead to the top board for just a moment, back up to our unit on dynamics, and use a little bit of F equals ma to find the acceleration. Once I do, then we'll go ahead and make this calculation. All right, so let's jump up here. I'm going to go ahead and do some erasing to give myself some room. And now let's go ahead and add up the forces here horizontally. So I have F pull, first of all, in the same direction as A, and then minus the force of kinetic friction in the opposite direction of A. So F pull minus F sub K is equal to NA. The force of kinetic friction is the coefficient multiplied by the normal force, and as we previously have noted, the normal force is equal to the object's weight. So let's go ahead and write the force of kinetic friction like so. Now let's go ahead and divide by the mass m to the other side of the expression to find the acceleration. Like so. All right, let's plug in the numbers and see what we obtain for the object's acceleration. So I have F pull, which was 15 newtons, and then minus 0.4 times 2 times 9.8, and then all divided by 2 kilograms. And this works out to be 3.58 meters per second squared. Okay, so that's just a typical dynamics situation that we saw in the previous unit. Now let's jump to the bottom board once again, however, to find the net work done. Okay, using the definition of the dot product now, we first of all have the magnitude of the first vector times the magnitude of the second vector, and then multiplied by the cosine of the angle between the two vectors. Notice that the angle between the acceleration vector and delta r is 0 degrees. Cosine of 0 is equal to positive 1, so this basically ends up being force times distance. Like so. And now let's go ahead and find this number. So I have then the mass of 2, and then times 3.58 for the acceleration, and then times 10 meters, which was the displacement. And this ends up being 71.6 joules, like so. Notice that this number here, however, is the same thing as the sum of these two numbers here. The reason for that has to do with the second way in which you can think of net work. Okay, now recall from F equals ma that the net force is the same thing as the sum of the individual forces. I'm going to use the letter I here as an index. You can think of this right here as force 1 plus force 2 plus force 3 and so on. And then what we do is multiply by the displacement vector delta r. In other words, what we're adding up here very simply is the work done by the individual forces, which we can mathematically write in the following way. This is the sum of the work done by the individual forces. So in other words, just add up all of the numbers that we calculated for the individual forces. So we have the work done by the normal force, which was 0, plus the work done by gravity, which was 0, plus the work done by these two forces here. Add these two numbers, and of course you end up with the same result, like so. Okay, let's note the following to conclude this problem. Write this down in your notes. The net work is positive, and the object in this problem is speeding up. We'll see the importance of this a little bit later on, but once again, for now, we're just doing practice calculations. Okay, now this was the first example, and in this first example, I kept it about as easy as possible. That is a horizontal displacement, so in fact, no work was done by gravity. Now let's take a look at our next dynamical example. This is going to be the basic incline with friction, and as we complete this problem, we're going to see that there is something special about the force of gravity. Now I'm going to go ahead and do some erasing here on the board first. Let's get rid of all of this. And then I'm going to have to move my file to the second problem for this lecture. All right, so let me move my file. Okay, let me go ahead and read the problem. Make sure you copy it into your notes. This is the basic incline, which we've seen before with friction. The angle of inclination is 30 degrees, coefficient of kinetic friction is 0.1, and the mass of the object is 1 kilogram. Calculate the work done by each force and the net work done if the mass begins at rest and slides 2 meters down the incline. So the situation looks like this. Okay, so here's the angle theta that's given to us as 30 degrees. Okay, the coefficient here of kinetic friction is given as 0.1. Here's our object like so. It initially begins at rest. It has an object of mass m equal to 1 kilogram, and then it slides downhill like so. It slides downhill like so over a displacement delta r. This displacement is given to us as 2 meters. And then at the end of the problem, the object ends up down here, and it does so with some speed v. Okay, now I'm going to, by the way, make a slight adjustment here on my diagram for clarity a little bit later on. Let's just say that the object begins at rest here at the top of the incline to keep things simple like so. Okay, now we just draw our force diagram to see the relationship between the force vectors and the displacement vector, and then we proceed through our work calculations. So as the object slides downhill and there is kinetic friction, we have the following. We have the normal force perpendicular to the incline, we have the force of gravity straight down like so, and then opposing the motion is the force of kinetic friction like this. Okay, let's go ahead and break up mg into its components. So we come down from the normal force and go across like so. Recall that right here is the angle theta. And let's also note that right here is the displacement vector delta r down the slope. The object will accelerate down the slope as well. And now we just proceed as before. So let's take a look at the work done by the normal force. So the work done by the normal force is the dot product between the normal force vector and the displacement vector, and then we just use the definition of the dot product. So we take the magnitude of the first vector times the magnitude of the second, and then multiply by the cosine of the angle between the two vectors. Notice that the normal force is still at a 90-degree angle with respect to the displacement delta r. Cosine of 90 degrees is equal to 0. So in the two examples that we've seen thus far, there is no work being done by the normal force. Is that always going to be the case? Is the work done by the normal force always going to be equal to 0? No, for the following reason. Okay, let me take my clipboard here, for example, like so to demonstrate. And then let me place my calculator here on the clipboard. And now, right now, there's a normal force vector acting upwards on the calculator like so. And then let's say that I do this. So then therefore, as I lift the object, the displacement vector delta r is in the same direction as the normal force vector. So then therefore, in this case, yes, work is being done by the normal force. But notice what is necessary for that to happen. I am necessary. If I am not there, is at any time the clipboard here going to start to push the calculator upwards? No. In order for work to be done by the normal force, I have to be present like so. If for all of a sudden, for example, the clipboard was to push the calculator upwards and I wasn't there, that would be magic. It would literally mean that the energy necessary to do that came out of nowhere. So then therefore the normal force will never do work because the normal force by itself does not have the ability to transfer energy. We'll get to that a little bit later on in greater detail. Okay, now before we get to gravity, and as I said earlier, there's something special about the force of gravity in this problem, but before we see that, let's take a look at the force of kinetic friction. Okay, so the work done by kinetic friction is the dot product between kinetic friction and the displacement. Once again, use the mathematics here of the dot product. So we take the magnitude of the first vector times the magnitude of the second vector, and then multiply by the cosine of the angle between the two vectors. Okay, as I've stated before, there's always going to be a 180-degree angle here between f sub k and delta r. Cosine of 180 is equal to -1. So we pick up our negative sign, like so. Okay, now to make this numerical calculation, let's replace the force of kinetic friction with the coefficient of kinetic friction multiplied by the normal force, like so. And then recall from F equals ma situations involving the incline what the normal force is equal to. Remember that the normal force vector here cancels out with this component of mg because there's no acceleration perpendicular to the incline. So as we've seen before, the normal force is equal to mg cosine theta for that reason. Let's go ahead and plug that into here. Like so. And now before I make this calculation, one thing that I want to clarify here, and you should note this later on when you review this problem, is that there are actually two cosines in this calculation. The first cosine was the cosine of 180 degrees that occurs here between f sub k and delta r. That's from the definition of work. This cosine here, however, this comes from F equals ma in noting that the normal force is equal to mg cosine theta. So make sure you keep track of which cosine is which as you review this problem later on. Okay, let's go ahead and plug in our numbers here to get our result. So I have negative 0.1 for the coefficient, then times the mass of 1 kilogram, times g, times the cosine of 30 degrees, and then multiply by the displacement of 2 meters. And this ends up being about negative 1.7 joules. Like so. Okay, and then lastly for the individual forces, now we have the force of gravity. So let's take a look at the work done by gravity. So the work done by gravity is equal to the dot product between the gravitational force vector and the displacement vector. And now we just use the definition here of the dot product to complete this calculation. So we take the magnitude of the first vector times the magnitude of the second vector and then multiply by the cosine of the angle between the two vectors. Take a look on the diagram above. Right here, this unnamed red angle, that's the angle between mg and delta r. Notice as the complement of the angle theta, it's 90 minus theta. Let's go ahead and write that here. Like so. And now at this point, if we wanted to, we could just go ahead and plug in our numbers and get our result. But as I indicated earlier at the beginning of this problem, there is something special about the force of gravity. In order for us to see exactly what that is, however, I'm going to do a couple of extra mathematical steps. Right here is a trigonometric identity. It's specifically the subtraction identity for cosine. And if you recall from basic trig, the subtraction identity is as follows. Okay, first of all, let me write these guys here, and I'll put it in brackets. We have the cosine of the first angle times the cosine of the second angle, and then there's a sign switch. It's plus the sine of the first angle times the sine of the second. Like so. Now in the first term, the cosine of 90 degrees is equal to 0. In the second term, the sine of 90 degrees is equal to 1. So then therefore, if you clean this up a little bit and do the math, what we end up with here is the following. Okay, take a look at that carefully. And now take a look at this right here. On the triangle above, what is being described right here as delta r sine theta? Well, delta r is the hypotenuse of this triangle, and then we're multiplying it by the sine of the angle. That's this side of the triangle right here is the opposite side of the triangle. The opposite side of the triangle is referred to as h in this context, and it's the height change. In other words, the work done by gravity only depends upon the height change h itself. That's vitally important later on in understanding exactly what is meant by potential energy. But we'll get to that later. For now, we're just noting it here. So here on the board below, this is hypotenuse times the sine of the angle. This right here is equal to the height change h, like so. This is very important. Let's note it here in your notes. So note that the work done by gravity depends upon the height change. As I said, that's very important later on when we eventually get to what is meant by potential energy. But for now, we're just seeing it here mathematically for the first time. Okay, now in order to complete this calculation, let's go ahead and find the height change. The height change, h right here, is just 2 meters multiplied by the sine of 30 degrees. The sine of 30 degrees is a half, so the height change here, h, is just equal to 1 meter. So I'm keeping the numbers here easy for this example as we proceed. And then therefore, the work done by gravity is mgh is 1 kilogram times 9.8 meters per second squared times then 1 meter. And this ends up being 9.8 joules, like so. Once again, with practice, this is easy to calculate. But now, as you're seeing here for the first time, and this is very important for later, the work done by gravity only depends upon the height change. And now let's just complete the problem to calculate the net work done. In order to do so, we'll just add up the work done by the individual forces. Okay, so let me erase here, like so. Okay, and now the net work done is equal to, first of all, the work done by the normal force, which was 0, plus then right here the work done by friction, plus then right here the work done by gravity. So 9.8 minus 1.7, this ends up being positive 8.1 joules. Once again, we'll note here that it's a positive number, and then like in the last example, in this example, the object is speeding up. So note once again that the object is speeding up. So in the two examples that I've done here in this lecture, all that we have done is we have practiced calculating work. The mathematical nuts and bolts of doing so involves the dot product. In the next lecture, then we'll start to get to exactly what it all means.